All right, so we're gonna go through and we're gonna do like the full video on this one right here. So we're recording it for all those people that decided that they're not gonna show up. So kind of like when someone decides they don't show up the day before, okay, they can still get the access. I'm gonna post this on my YouTube. So now, when I kind of need you guys to pretend like you're excited to be here. Yay, good. All right, that's good energy right there. So when I say class, everyone should say yes. All right, so, but, okay, so you guys ready? Yeah, we're gonna practice this. So, class.
Yes, sir.
Not bad. All right, let's try it again. Class.
Yes.
Yes. All right, so now, okay, now we're gonna get really fake on this excited right now, all right? You ready? All right, so class.
Yes.
master. Thank you. All right, so we are gonna build a popsicle bridge. Yay! All right, popsicle bridge.
I actually don't want to do that. No, actually, I don't know.
All right, real world application. So, all right, lengthwise sky pedestrian bridge in Malaysia. It is 125 meters long, 1.8 meters wide, designed as a curved walkway to maximize the viewing experience. I don't know if do you guys like heights?
No.
I don't care for heights. I do. But what they did is through the mountains like that. So it's pretty. You see people taking pictures and you see people like on the glass walkway part, just like completely freaking out because you see way down. It's hilarious.
Mister, have you been there?
No, I have not. So formed a steel concrete panel set on top of an inverted triangular truss. So you see right here, we got the truss right here. Suspended by 8 cables from 81.5 meters high, single pylon, and hangs out about 100 meters above the ground. Designed to carry a maximum capacity of 250 people. Not bad, right? Okay, just getting there is actually the hardest part. So, next one. Florida International University pedestrian bridge collapse. Uh-oh. A poor design led to the collapse of pedestrian bridge under construction at FIU in 2018. Engineers incorrectly calculated the amount of stress the structure could take. Now, when engineers make a mistake, this happens. When mathematicians make a mistake, no one cares. No one actually goes back and checks mathematicians because their math calculations don't really have a real world application. So physics and engineering is applied mathematics. So math is the basis for this. So if you are messing up your math, got to be careful to not mess up the engineering because you have to check and double check for all these things. That's why there's guidelines and all kinds of stuff in place. All right, design challenge. It is your team of engineers working to design a bridge using glue and 200 popsicle sticks or less. 200 or less. I know I have a little thingy here somewhere. I don't know where it went. Is it the other one? Oh, there it is. Oh, did it go? Did I go too many?
No.
Okay, this is just one, right? Okay. Criteria, bridges must be able to hold 20 pounds. With popsicle sticks. 20 pounds. So, structure must span a minimum of 14 inches in length and be 16 inches long. Why can't it just be 14 inches long? Go ahead.
I don't know. Because it's a distribution. So.
And the span, so that's your gap, is 14 inches. So the gap is 14 inches, and so 16 inches means you have 1 inch on both sides of the gap. That's what that means. So when you guys are going through and designing these things, that's things that you have to take into account. So the whole thing itself has to be that long. Okay, constraints. Can use no more than 200 popsicle sticks, can only use Elmer's wood glue. I have that in the back. Okay, can't use any like super crazy like industrial glue or anything like that. So just that. Did that work?
He's going forward.
Trying to. Okay, we did criteria. There we go. All right, materials. 200 popsicle kits, sticks, wood, craft glue. Testing materials, 5 pounds at a time. We're going to do 5 pounds at a time. And there is going to be a trophy for the most weight out of all the groups. So it's 2 groups here, and there's 2 groups in my 6-hour class. So you're going to be competing with everyone. Yes?
What kind of trophy is it?
It's a pretty awesome trophy. Would you like to see?
Yeah.
This is not the exact trophy.
Oh, that's cool.
Yeah, so I was testing out how I was going to do the trophy. It's actually a blueprint on acrylic. So if you guys want to see it, you can take a look. Anyway, so I like trophies. You get a nice little reward that you can actually put in your Avid blah blah blah. You know, highlight of my high school careers. My bridge held up 9,000 pounds. Probably not, but still, right? Okay, so 2 chairs, desk, or small table, enough to allow for design to be suspended 1 foot above the floor. So I'm gonna build something. There's gonna be a gap. So if I was using the two chairs model, it's not gonna be this, but I'm trying to explain to you. All right, so it would be like this, and as it's 14-inch gap here, and then holding up, so you could at least have an extra inch on either side that is supporting it. And then I'm going to put weight directly on the center in 5-pound increments. And to get a passing score, you got to have a minimum of how much? 20 pounds. Okay, minimum 20. But that's what it means about the span and being able to suspend it. I do have a thing over there that I set up to actually do this. So we can put it over, and it's probably not going to be 1 foot. It's probably going to be like 8 inches, because if we have like 100 pounds on something, you know, crashing down a whole foot is going to cause more damage. So yeah, that's why I make it less. And just so you know, it wasn't last year, it was the year before. They came up with 150 pounds. I had to go to the gym to go get more plates. There was a bunch of plates of weight on this thing. That's crazy, right? So, that's your goal. Okay, before we get started brainstorming, consider the following. Different types of bridges. So, your assignment, which you guys are going to start off with, is in your engineering notebook. Right now, your entry for today is going to be your popsicle stick bridge. Popsicle stick bridge. Then we're going to start listing out the things that we're doing. So in the whole process, we have a design process that you're going to follow. There is something in your notebook that looks a whole lot like this. Yes? It should be in that first. Open your book. It's right there, right? Kevin, yes?
Oh, that thing.
That thing. This is actually the design process. So I'm going to go through item by item right now. So starting out, what it says, ask, identify the needs and constraints. From what I've told you so far, what are the needs and constraints? You need to do what? What are you building?
The bridge.
There you go. That's your need. You're building a bridge. Your constraints. What do I need to do with that? To build a bridge, what's the rules and guidelines? 200 popsicle sticks. What else? The glue. Anything else? The length, right? There you go. And it has to fit the gap of 14. Very good. I am going to go back on it. Okay. So these are what we're talking about here. Now, different types of bridges. So you're considering these. Which shapes are stronger than others? Amount of weight your design must hold. Okay, that's another constraint right there. Your minimum is how much? 20 pounds. 14-inch span criteria. Aesthetics. What does the word aesthetics mean? Yeah. Does it look good or does it look like doo-doo? You want it to look good, right? Okay, good. So we want it to look good. And efficiency. Try not to use all the popsicle sticks. I've had one group do this, but they still pass, but they really hurt themselves just by trying to be more efficient. The 200 is the maximum, and that's what everyone that's successful actually used. I had one group, like I said, try to go less, and they didn't do very well because of that. So if they would have added more support with the extra, then they could have added more. Or they could have had more weight. All right, testing process. 2 chairs, flat surface. This is what it looks like right here. So we can start doing it in increments, and I'm going to give you the 5 pounds to start to make sure that it is going to hold your 20 pounds. We're going to have this project over a course of several weeks. So as we're building, you guys are coming in, trying it out, building it, design process. Now, right here, this is going with this. Keep adding weight. Okay. We're not going that far yet. Okay. Discuss, makes a bridge aesthetically pleasing, develop a list of attributes. Judge bridge design aesthetic value, scale 1 to 5. Okay. Give 1 positive comment, 1 suggestion for improvement on each design. This is at the end. Okay. You will reflect and debrief. At the end, you will reflect and debrief. You're going to actually say, what did you guys do good? Did you work good together? Is there things that you need to work on? What can you done better to improve your bridge? Okay. Now, these things right here, engineering design process. This is where we're starting our notes. Right now, today, you are inserting. So in our notebook, you start any entry with the date, the objective, which is engineering design process, and this is going to be over what? Popsicle bridge, right? So Popsicle bridge. Where's your notebook? Why? Huh? Oh, it's at home? Okay, so you do have, but not here. Yes. Okay, that's what I was looking for. I was worried. Okay. So engineering design process, we're going to go through. And you have this in your notebook already at the front, so reference it always. So, I said the first thing, ask. That's unnecessary. Right here. So they call it different things, but the way the one that we're using says identify the problem, which is my ask. Okay, identify needs and constraints. So step 1, we said we're going to do what? We're going to build a bridge, and our constraints are we have 200 popsicle sticks. What else do I have? The length, 14, maximum 16, right? Okay. It's got to cover that span. What else? wood glue,
and
and it's got to be pretty strong, right? Minimum of
20.
20 pounds. There we go. Now, I've already put you guys in the teams that you guys are going to use for this. This is your teams. 2 is going to be research the problem. I gave you an idea. Now it's time to do research. Research requires actually looking stuff up and seeing what other people have and looking for bridge ideas. In your notebook, as you add these ideas, right now this whole brainstorming thing, it's not supposed to be neat and organized. Put all the ideas that you guys come up with. Add them to your notes. Be like, hey, in my notes, I have 5 different sketches of different bridges that we could build doing the same method. Sketch it out. Write it out. Talk about the different bridges. Look up what is important, what shapes, what type of bridge is going to give me the best for what I'm doing here. Now, as you brainstorm, each person individually should brainstorm because everyone's going to come at it from different directions. So if you have an idea, it's probably going to be different than your neighbor's idea, but when you come together, you guys can talk it out to actually see, oh, hey, yeah, good point, bad point. That's why you're actually writing down notes to go along with this. So this type of bridge is going to work good for what I have for what reason. Everyone's looking up different things. Everyone should have some research in their notebook. Everyone should have research in their notebook. Okay, then brainstorming. Okay, which one are we on? So research the problem. Imagine. So this is where you come together. So everyone has brainstormed. You guys come together with all the different ideas that you have. Develop possible solutions as a group. So as a group now, you're going to come together and actually say, hey, I want to try it like this. I want to see designs. I want to see sketches of what you would do, how you would do it. Your engineering notebook is graph paper. Use the graph. Try to make it to scale. Try to actually scale it out. So if it has to be 14 long or 16 long, make 16 squares. That is a way of actually doing it, so it would be to scale. So that would mean that 1 square is 1 inch. In your graph, 1 square, 1 inch, draw it out. Then you could actually make things to be able to scale, to model it out. That helps. Choose best solution. Over here, plan selecting promising solutions. So out of the group of what you guys decided of everything, everyone come together, because this is where Imagine is. You're coming together and talking about what it is that you do. You might come up with 4 different solutions. Come to a consensus as a group, because as a group, you have to decide what it is that you're going to build. That right there is your select your promising solution. After that, we're going to create. That's when I'm going to give you your first set of materials. I'm going to give you your glue. I'm going to give you the popsicle sticks. I'm going to give you a bed to hold all your stuff in. And yes, you can cut them. There is going to be like a little X-Acto knife to be able to cut the popsicle sticks if you want to do that. You can. So that's going to be create and build your prototype. Test. After you build it in the first place. This is what happens a lot, which I get frustrated about. A lot of people put everything off until the last minute. If you have until Friday to build something, they finish it Friday. The problem is it should have been finished Thursday. You test it to see if it works, and then approve it for Friday. If it doesn't work very well, on Thursday, you have time to come back and fix it, correct it, or make improvements. That's the point right here. A lot of times, I'm telling you, not here, I'm saying in general, A lot of students miss out in these two right here. They just build a prototype and call it it because they wasted all their time up into here. You have to get to this one right here, to the redesign. Because if it smashes, we need to actually try it, start over again. I shouldn't see anyone fail on test day because you already tested it to make sure it is going to work, and then you improved it to try and make it better, and you tested it again. After you test and improve, okay, let's say it fails. Pablo, let's pretend like yours is going to fail.
All right.
Right here, bam, evaluated. It failed. It only held 5 pounds. Redesign. Now, to do the redesign, identify what you need. So we go back in the circle again. So identify what we need because our prototype failed. Okay, we need to focus on doing what? Are we going to change the whole design, or are we going to change the way that we put it together? Right there. That's researching problems to go along with it. As you come back around, this is over and over again. You keep going over and over. After you test it, improve it. Keep going. Improvement. Productive failure. Engineering design process involved production failure. Test, fail, redesign, repeat, iterate again and again until you have the best possible solution. It is important to document iterations, keep track of each redesign in your notebook. As you go, document everything. So in your notebook every day, you're going to start a new entry for this day. And you're going to say, okay, what did we work on this day? Right there. This is teaching you how to use your engineering notebook. Do not cross out. Do not actually don't try to erase anything. That's the reason why I'm having you guys write in pen. Don't try to erase anything. Don't just scribble it all out. If it doesn't work or you made a mistake on something, leave it there. Reference it. Say, all right, on this day, it did not work. We tried this, it did not work. There we go. So, and continue in there on the steps that you did. You should have a step every day. Should have something that you're doing in a group. So, use engineering notebooks to sketch ideas, documents, iteration, any measurements and or calculation. It is also important to showcase the fact that there can be multiple solutions to the same problem. There is no one right solution. Okay, there's all kinds of different bridges for this. Now, some of these things, the vocabulary, so I want you to add this because this is important. The reason why this is important because you're going to do some research right now and you're going to see these words. And so let's say, for instance, my name is Kevin. I'm writing these down because they are in my notebook, because when I do research on bridge designing, it's going to say abutment, which is part of a structure that receives pressure. Okay, aesthetic, appreciation, beauty, and appearance, what it looks like, right, Kevin? Are we writing these down, Kevin?
Yep.
Okay, so do you need a pen, Kevin?
No.
No. You have it, right?
Yeah.
Okay. Arch. A curved shape, an arch bridge is shaped as an arch and is naturally strong. Beam. A long piece of heavy, often square wood or steel used for construction. Beam bridges are horizontal beams supported at each end by piers. Cables. A strong wire or metal chain. A cable-stayed bridge is held up by cables. So that bridge that we saw a little while ago, the Chinese one in Malaysia? Yeah, that one right there, that one had cables. Cantilever. A horizontal beam that are supported only on one end. Cantilever bridges are built using cantilevers. So it's only on one end. So it's supported on this side, but not the other side. So I'm going to come back to this. So if you're writing down, it's okay. I'm just trying to get it for the video. So I will go back. I'm just going to So if you're watching the video, just pause it, write it down. I'm just going to go through the list so I can finish this so you guys can start on your research today. There we go. So the next set of vocabulary for those people watching, go ahead and hit pause right here to go over it. Constraints, limitations with material, time, size, team, etc. Criteria, conditions that the design must satisfy overall. Critical load, weight in which that the building or structure fails. Engineers, inventors, and problem solvers of the world. 25 major specialties are recognized at the end of this. Engineering design process engineers use to solve problems. Engineering habits of mind, 6 unique ways engineers think. Iterations, test and redesign is one iteration. Repeat, and it's a multiple iteration. Load, a weight or source of pressure put on an object. Prototype, a working model of the solution to be tested. Span, the spread or extent between supports. Suspension, hung in mid-air, suspended bridges are suspended from cables and tend to be long. Stress, pressure or tension exerted on a material or object. Truss, group of beams forming a triangle-shaped, rigid framework. Truss bridges have solid deck and lattice of pin-jointed girders for the sides. All right, so right here, you could actually go through and find stuff for this. Engineering fields, okay. For this, you want to look through here, go ahead, pause it. There's actually all kinds of things and types of engineers, not just, material and building bridges, but you could be chemical, you could do all kinds of stuff. And I think that's it. Engineering habits of mind. So for this right here, it is about how engineers think every day. Core engineer mind is about making things that work and making things work better. So right here, habits of mind. So curiosity, open-mindedness, resilience, resourcefulness, collaboration, reflection, ethical consideration. Now, in right here, engineering habits of mind, system thinking, adapting, problem solving, creative problem solving, visualizing, and improving. Now, care engineering mind, making things that work and making things work better. That's the goal of everything that we're trying to do. Try to make something work with what you have, or you have something and you make it better. Kind of like the phone idea that I was telling you guys about when I did the iterations for the phone stand. It's already exists. I just try to make it better. And that should be it. So make sure you like, share, and subscribe. And I'm going to stop right here. Where is, there it is.